Alright guys, hello and welcome to today's class. I'm Mr. Ludden and today we're going to have a look at functions. This is a follow-on video from the one I did on patterns, and the reason I've done that is because there's a huge link between the two. Oftentimes in your exam you could have a patterns question and a functions question, and they might be more or less the exact same thing, except it might be worded just a small bit differently. There's a huge overlap between the two. Today we're going to have a look at identifying functions, what they look like, and how they come up in graphs, I suppose. My next video is going to be about graphing functions and actually drawing your graph yourself, but today is going to be just about functions. If you can wrap your head around functions, it's a huge step, because for your whole paper 1, some of your paper 2 as well, because they do come up quite a bit in different areas. So that's what we're going to have a look at today. We're going to jump straight in with a definition of functions, and as with all definitions and our key points, I will have these in the description below, as well as the link to my patterns video as well. So if you are making notes, all the notes that you need are in the description, so you can just sit back and listen, I suppose, and you can take those down at the end. That's the best way to get the most out of this video. I will be, for some of the questions, I will be giving you prompts to pause the video and try the questions yourself, and then I'll do the solutions, and in that way, as I said, you'll get the most out of the video as well. Okay, functions. Functions, as a definition, is a relationship between a set of inputs and outputs. So every input has only one output. So I'm going to highlight that bit there at the end, because that bit there is so important. To show that in a diagram, I've drawn a set of inputs here, the numbers 1, 2, and 3. Drawn a set of outputs, the numbers 11, 12, and 13. And as you've seen, I've drawn arrows between certain pairs of numbers. So as you can see, I've joined 1 and 11, 2 and 12, 3 and 13. The correct terminology there, and I'll just write that down, is the number 1, it's not joined to 11, it's mapped to. Just put that in inverted commas. It's mapped to the number 11. The number 2 is mapped to the number 12, and the number 3 is mapped to the number 13. So as you can see here, each one of my inputs only has one output. So the 3 pairs of numbers. That right there is your definition. That right there is your classic scenario. This right here is a perfect example of a perfectly working function. But I'm going to give you 2 scenarios where they mightn't necessarily. It might be a diagram that looks very similar to this one here, but it mightn't actually show a function. So we just got to be ready for that. These are my 2 scenarios. In my first one here, I have A, B, and C in my inputs, and I have D and E in my outputs. And in my second one, I have W and X in my inputs, and I have T, F, and O in my outputs. So we'll look at our first one first, and I've written out my definition just up here again. We have to decide, are these functions or are they not? So I'm just going to get my red pen. For my first one, excuse me. For my first one, you might think straight away that, oh, well, my first one here doesn't look like the example that I had in the last slide, which is this one here, because 2 of the lines here are going to the same number, this one and this one. So A is being mapped to D, and B is also being mapped to D. So you might be inclined to say, well, no, that's not a function because you can't have that. But if you look a small bit more closely at our definition up above, every input has only one output. Let's look individually at our inputs. The letter A here only has one output, D. The letter B only has one output, the letter D. It doesn't matter that they have the same output. There's nothing in my definition that says you can't share an output. So this scenario here, A is fine, B is fine, and of course C is fine down here. C is just being mapped to E. The C and E pairing here, that wasn't my problem. I had to sort out what was going on up here. So this right here, even though it looks a bit strange, that right there is a function because each of my inputs only has one output. Slightly different scenario over on my left hand side. I have W going to T, I also have W going to F. So in my WTF scenario up here, my W, my input, has two outputs, T and F. So in this scenario, my W here, I'm going to put a little X over that to signal that it's wrong. I cannot have two outputs. This does not describe a function. Down below, this part here is fine. XO, my XO part is fine, but my WTF, as the name suggests, I cannot have that. There's something wrong there. So for that one there, I'm not going to do that in highlighter. I'll do that in red. That right there is not a function. So we need to be aware of those. We're going to have a look in a minute about how this exact thing comes up in an exam question. But just before that, I need to have a look at some of the vocabulary used to describe inputs and outputs. They won't always use those words. So we're going to have a quick look at vocabulary. Then we're going to have a look to see if you can answer a junior cert question with literally the bare minimum piece of information about functions. Okay, our vocabulary, our inputs. I've drawn the same set that I did in my first slide. And as you can see, my inputs are here, my outputs are here. They mightn't call these your inputs. They might call it your domain, and they might call it your values of X. So I've put those in a box just below here. They're written in black ink. For my outputs, let me do that in a different colored highlighter just so we can be totally clear. Let's go green. My outputs can also be called my codomain or my range, and the letter that is associated with my outputs is the Y, or sometimes F bracket X bracket. This is called FX if you are speaking it, or sometimes F of X. So if I say the word FX, or if I say F of X, you know that I'm referring to the F bracket X bracket. Now, what you, as an aside here, what you might be asked to do is describe the relationship between your inputs and your outputs. Now, as you can see, if we took our first pair in here, and this is where my vocabulary sort of comes in. To get from 1 to 11 mathematically, there's a couple of things I could do. I could add 10, I could multiply by 11, and then I could do some more complicated stuff. But the main ones there that are jumping out at me are the add 10 or multiply by 11. So I have two choices there, but two choices isn't good enough. I need one choice that works for not only my 1 and 11, but also my other pairings. So I'm going to see if which one of my options there works with my other two pairs. So for my 2 here, if I multiply that by 11, I'm going to get 22, which doesn't work for my 12. Because 12 is not the same as 22, obviously. However, if I add 10, I will end up on 12, so that's fantastic. And adding 10 will also work for my 3 and 13. So I know that my rule here is to add 10. So just put that up top. 1 plus 10 will give me 11, 2 plus 10 will give me 12, 3 plus 10 will give me 13. And that plus 10 there is important. It's essentially the rule that gets me from my inputs to my outputs. And that's basically what functions are. Now, if we were to write that out in an English sentence, we would say that our outputs is equal to my inputs plus 10. So if I take the first scenario here, my output was 11 is equal to whatever my input was, which is 1 plus 10, and of course we can see that that's correct. I could say that my 12 was my 2 plus 10, and of course that's correct, and my 13 was my 3 plus 10. So my rule here was that my output is equal to my inputs plus 10. And these are my 3 examples. I'm just going to take those away because that was just to show you how those work. In your exam, they won't write your question like this. And this is where people get a small bit confused. They see X's and Y's start coming in, and if you don't keep your head about you, sometimes people can lose their minds just a small bit. Your outputs. Remember about a minute ago, I said that outputs have some different names. They can also be called your codomain or your range or your Y or your FX. In maths, in functions especially, we like to use symbols or letters instead of saying outputs. We could say that your range or your codomain here, but again, we'd just be substituting a word for a word. For my outputs, this is the same thing as my FX. So I've just taken out output, and FX means the exact same thing, is equal to my inputs. Now I don't want to say the word input, and I also don't want to say domain because that's a word. I'm going to say X is equal to X plus 10. So what you've done here is you've gone from English words like that describe what's going on here in your set. Your outputs is equal to your inputs plus 10. The mathematically correct way of saying that, writing this as a function, is that f of x is equal to x plus 10. This here describes exactly what's going on over here. And you need to be aware, that's the reason I took a break from like the sort of questions to give you your vocabulary here. It's because knowing that your input is also called your domain and your x values is so important to be able to answer your question, in the same way that knowing that your output is also called your codomain, your range, your Y, or your FX. If you don't know those, then it'd be very difficult to know what they're actually asking you in the question. So I cannot highlight how important that bit there is enough. Okay, I went a small bit off track there, but this is all vital stuff. We were going to have a look at, with our vocab now, we were going to have a look at how this question that we had done, how it came up in an exam question. So we're going to take our knowledge from this, what our function is. We're going to take our knowledge from our vocabulary, so whatever's in my black writing here, and we're going to have a look at the question that came up in 2017, question 15 on your paper 1. And it's a question about graphs. It says 3 curves, A, B, and C, are shown below. 2 of the curves, just 2 of them, show a function of x. So you can nearly see where this question is going. They want you to show which curve does not show a function of x. So this is linking into sort of like our coordinate geometry, and I will do a video on that at some stage as well. Now remember, input for a function, input only one, output only one. So if I was to switch up these, my inputs are my x's, so my x's can only go to only one y. If you remember from my definition here, my a lot of writing, my outputs is also called my y, and this is going to help us in relation to the question. Okay, so that's my rough work over here. Every x has to go to only one y. So let's see if that's the scenario in graph A over here. If I take any point x on the x-axis, and if I draw a line up, you can see that it's only going to hit my graph once, right there. And if I wanted to find the y value, that would be the corresponding y value over here. If I took it from here, if I go all the way up and all the way across, well, the same thing happens. My line would only touch my graph once. And that's going to happen no matter where you do it. So this one right here is a function, because each of my values for x, well, only hits the graph once, therefore only correspond once to the y-axis. The same thing happens in B. I know it looks a small bit different, the graph, but if I put a line up and a line straight across. It's only going to hit my graph once. There and there. Only going to hit the graph once. Here and here. Only hit the graph once. Here and here. Once. As you can see, the graph, any value of x, if I draw a line up or down, if I go across to the y-axis, it's only going to hit it once. So b is going to be a function as well. For part C over here, however, it's a small bit different to what went before it. And I will take away my red lines at the very, very end, just to, I suppose, highlight that at the end. If I went at graph C the same way as I went at graph A and B, what I would end up with is, well, that's fine. That only has one value of y. If I went over here, this would only have one value of y. But what happens in the middle is the interesting bit. If I went, I'm trying to pick the best spot. If I went here, and if I drew a line straight up, my line straight up from this point here on the x-axis would hit the graph here. So it would have one value of y. It would also hit it here, two values of y, and it would also hit it here. Which would mean that for one input, for this input here, I'm going to have 1, 2, 3 outputs. Now we know that for every input you can only have one output, so C here is going to be our answer. And the reason, make sure to give a reason, every input can only have one output in a function. In the case of graph C, in this scenario here, when I drew a line up from this point, my line up from the x-axis would hit the graph once, twice, 3 times. I cannot have 3 outputs for the same input, therefore that is not a function. In an exam question, this sort of can sometimes come up as, mostly comes up as an A part or as a small part of the question. Your answer is going to be either yes or no, or in this case tick the box, but your reason, which will get you the next part of your marks, your reason is going to be the exact same as what I've done up here, the first slide. Your reason is 99% of the time that thing right there. A function is a relationship between a set of inputs and outputs, so that every input has only one output, and that's more or less what I've written down here. So guys, just make sure that you're 100% clear on that. Guys, just taking the red marks away from this question, and just gonna make one more attempt at it. You could have made a guess at this even if you didn't know, like which one is the odd one out. Well, like this one here is nice and smooth. It's going like from left to right. It's going like, I suppose, I'm trying to think of another word for smooth, but it's nice and it flows, I suppose. This one here flows as well. This one here, it doubles back on itself and then goes on again. So if you're looking for the odd one out, like C there is the odd one out. So if you ticked C but didn't put any reason, you'd be getting maybe 2 out of your 5 marks there. But your reason, like that's an awful handy way to finish off your question to get your full marks. And it's just a matter of knowing that sentence right there. I can't highlight that enough. All right, we're going to have a look at how the different types of functions now. Again, linking to our patterns question, the 3 ones are linear, quadratic, and exponential. But we're going to have a look at how to recognize those just from our functions. So just from seeing something like f, just actually if I just go back here, just like seeing something like this here, fx is equal to x plus 10. Well, what would that look like on a graph? That's what we're going to have a look at next. Okay. In a functions question, you may be given a function that looks something like this. This is the general form of the function. So fx is equal to ax plus c, where a and c are going to be numbers. So the a and the c here can tell us pieces of information from our graph. So I'm just going to take my a over here. So even without graphing my graph, I can tell what this is going to look like. First of all, we know that this is going to be linear. I'll just take my a away there, because I don't need that just yet. We know this is going to be linear because the highest power of x is just x, or x to the power of 1. I'm supposed to give it its full name. We never write the 1 though. So it's written like something x plus something, where the thing before the x and the thing at the end here, the a and the c, those two are numbers. It'll be written like that, but the way we know that it's going to be linear, so like a straight line, is the x on its own here. It doesn't have an x squared. It doesn't have an x cubed. The highest power of x is just x itself. So I'm going to write that out. Highest power of x is x to the power of 1. So that right there is x to the power of 1. I will be doing a video on indices as well at some point, but that right there is your definition for what a linear function will look like. So an example of that might be, and I'll do an example up here just to give us some context. Fx is equal to 3x plus 2. So this right here, it's in the same form as my general one over here. And in this case, my a would be 3 and my c would be 2. And in this function here, my 3 and my 2 tell me things about this graph. Okay, so I'm going to take the a first. If a can be one of two things. It can be either positive or negative. So if a is positive, as you can think, it's going to be a straight line. So if a is positive, my graph is going to go up. If a is negative, you can probably guess my graph is going to go down. So for this one up here, my fx is equal to 3x plus 2. My 3 here is positive, so I know that this graph is going to go up like this. Something like that. For my c, I'll just get my red pen back. For my c, let's put it, oh, I don't want that. How do I get back? Okay, apologies about that. My screen went a small bit berserk, but we're back. I was talking about the c. The c here is something called my y-intercept. So let me put that in the same shade of navy. So we're going to have y-intercept. So it's where my line is going to cut my y-axis. So I'm going to do a small sketch here in the bottom right corner of what this up here is actually going to look like. So if I was to draw out a quick coordinate plane, so this is very, very rough. I know that my line is going to go in an upward position, and I'll just highlight that. I know it's going to be positive, and I know that the y-intercept is going to be 2. So I'm just going to mark, I'm just going to get my red pen. I'm just going to mark my y-intercept first. I know that my y-intercept is going to be 2 in my situation up here. So I'm going to mark 2 up on my y-axis. Remember, this is my y-axis, this is my x-axis. Up 2. So that's 1, that's 2, 3, 4, 5, 6, 7, 8, 9. And I know that my graph is going to go up in an upward direction. And if you're comparing this to our coordinate geometry, it links very, very heavily in. You might have seen something along the lines of y is equal to mx plus c, and I'll be doing a coordinate geometry video in a bit, which links our functions and this here, which is coordinate geometry. You'll notice that my 3 here will be my m, which, if you remember, it's here the slope of your line. So that slope of the line is going to be 3, so it's going to be quite steep. It's going to look something like that. For today, we just wanted to know the y-intercept, so I'm just going to highlight that, and the fact that my line was going up. I sort of went off on a tangent there with my coordinate geometry, but it's no harm for you to be able to see the link. If you can't make the link out between those two, then no worries. I will be doing a video of that at some point in the next week, so just keep tuned for that. The main thing here was that my function here, my function up top, it was going up and positively, and it crossed the y-axis at 2. Those were the main points I could take out of that. Okay, so they're my linear functions, and again, I will have all of these a lot neater at the bottom in my key points in the description. I'll also have it on the last slide, and I'll have a talk through those. So this is just sort of like my rough work here. The next sort of function that you might be given looks like this, and this right here is a quadratic, and again links back to my patterns. Quadratic looks like something x squared plus something x plus something, and again in this scenario here, my a and my c are going to tell me things about the graph, and then I'll just give you one more piece of information that links with your factorizing, that will give you another piece of information about the graph. Let's have a look at what a says. So a, and again I'm going to do this. So remember, a is just a number, and a can either be positive or negative. So I suppose just before I do that, actually, seeing as I started off my linear one with this fact here, if the highest power of x is x1, then what I should be saying here first of all is that the highest power of x, as you can probably see, so for quadratic, highest power of x is 2. In other words, it has an x squared in it, and it doesn't have anything higher than x squared. It doesn't have an x cubed, it doesn't have an x to the power of 4, it doesn't have an x to the power of 1 million, for example. So that's how you know that this is a quadratic, because it's going to have an x squared in it. So just back to my a, just what I was saying, my a here in front of my x squared can be positive or it can be negative. If it is positive, it's going to impact the shape of the graph. You'll notice that this this function here is different to my linear one. So it's not going to be a straight line. It's going to be a curve, and it's either going to look like this, or like curve down, up and down, or it's going to curve down and then up. And my a here tells me which one it's going to be. If my a is positive, then my graph will always look like this. It'll look like a smiley face. So I'll just put my eyes there. And the way we remembered it when we were in school was, well, if a is positive, positive is a good thing, you're going to be smiling. If a is negative, well, that's a bad thing, so you're going to have a frowny face, and there's your frowny face. So whatever your a is, if your a is positive, your graph is going to be smiley. If your a is negative, it's going to be like a frowny face, like an N shape. I'm going to go on to my C. I'm going to skip ahead to my C, and then I'll loop back and we'll talk about B in a minute. But these are all clues as to what your graph will look like before you even start to graph it. So for B, oh no, I said C. I said I'm going to do C first. For C, the same as my linear ones. This is going to be my y-intercept. So it's going to be where my graph crosses y-intercept. It's going to be where my graph crosses the y-axis. So I might just draw a quick graph here. If my graph looked like this, well, my C would be this part here. So let me just draw right there. That's going to be my C, where my graph crosses the y-axis. All right, and one more note. For my quadratic functions, if you link this back to your factorizing, if you factorize your quadratic, you will get two values for x. Two values for x. These two values of x are where your graph is going to cross your x-axis. So these points will be your x-intercepts. Okay, so quite a bit to take on board there with that part there. The main two things with this is my A and my C. The A, if it's positive, smiley face. If it's negative, a frowny face. The C is your y-intercept. It's where it's going to cross your y-axis. And this part over here, I'm going to give you an example or show you an example of how this works here. So, and we'll come back and have a look at our exponential functions in just a little bit. But I'm going to skip ahead here. You may have used Geogebra before. So for Geogebra, it helps you graph functions. So it's excellent to use to check that your homework is correct, or just to see what a graph might look like and that you're not sure of. So I've taken a screenshot of a bit of work that I was doing on Geogebra before, and I just want to highlight one, maybe two things. So for your, we're just going to have a look here. And I have a link for Geogebra in the description below. Very, very handy to mess around with, as I said. So for this here, I'm just going to concentrate on this part here. So this part here, gx is equal to x squared minus 5x plus 6. You'll notice that this is a function as well. I know I said that our functions are usually fx. Sometimes they can be called gx, hx, zx they could be called, but usually they keep it either f, g, or hx. It means it's just the name of another function. So gx is equal to x squared minus 5x plus 6. That's what we've put into our function box over here. And it's done a graph of that function for you. And our graph of that function is the curved one here. And we know that for two reasons. We know that for x squared here, that's the same thing as 1x squared. So if I was to compare this to the general form of my quadratic, I have x squared plus bx plus c. We know that my a, if my a is positive, which it is, I know that it's going to be that sort of shape, which lines up with exactly what's over here. I know that the 6 here, which is my c, I know that that is where it's going to cross the y-axis. And if I check the y-axis here, remember that this is the y-axis, the vertical one here, it does cross it at 6. So we know that that is correct as well. So we know that that's lined up. So our first 2 points from our last slide, which was this one, we have applied those to this question. My A was positive, and my y-intercept was my C, as we've seen over here. Now, the thing I was talking about, the last point here, was if I factorize my quadratic, well, what does it tell us? So I'm going to factorize my x squared minus 5x plus 6. And there's two main ways of doing this. You can do this with your minus b formula, or you can do it with your guide number method. And I will be going through those two in a future video. So just stay tuned for that. For now, I'm just going to do this with my guide number. So 1x squared minus 5x plus 6. Well, my guide number is going to be my 1 times my 6. I'll just have a bit of rough work here. 1 times 6, which is 6. And for this, I'm looking for factors of 6 that will add together to give me my minus 5 in the middle. That's going to be minus 3 and minus 2. So what I'm going to do is I'm going to keep my 1x squared there. And let's make sure that that's squared. 1x squared there. I'm going to keep my plus 6 at the end. And instead of my minus 5x in the middle, I'm going to put minus 3x minus 2x. This is now a grouping question. So we sort of change it from a quadratic. It's still a quadratic, but it looks more like a grouping factorizing question. So what I'm going to do is I'm going to split that down the middle. I'm going to get the highest common factor here. I'm going to say that that's x and x minus 3. And on this side over here, I'm going to, the highest common factor is minus 2. And I'm going to have x minus 3. And if I finish off my factorizing, I'm going to have x minus 2 and x minus 3. Now, if I want to find out where that crosses the x-axis, I suppose like the full term for that, or just to finish this off, this would be equal to 0, and I'll show you why in just a little bit. So that's equal to 0, that's equal to 0. Now at the end here, if this times this is equal to 0, well, it means x minus 2 is equal to 0, or it means that x minus 3 is equal to 0. For my situation over here, well, that means if I add 2 to both sides, I'm going to have x is equal to 2. And on this side here, if I add 3, I'm going to have x is equal to 3. Now you might think, why did I do all of that work? If you notice, x is equal to 2 and x is equal to 3, like that's the mathematical part of that. But if you look over to your graph, those 2 points where x is equal to 2 and where x is equal to 3, that's where your graph crosses the x-axis. So that ties back into what I was saying about your quadratic. If you factorize it and if you find your roots, so these right here are your roots, where that applies to your graph is that it's where your graph crosses the x-axis. So this part here, this part here is your C. You know that it's this shape because A is positive, and you know from 2 and 3, you know that these are the roots when you factorize it. So even before you go graphing any type of function, or especially quadratics, you know like so much information about your graph already just from this small piece of information. Again, the link for Geogebra is going to be in the description. Please do use it. Please do mess around with it. It's a great tool to have. Okay, we've done linear graphs, linear functions even. We've done quadratic functions. The last one we're going to have a look at is exponential functions. And this is one where my exponent, the x, the power, changes. So in your junior cert, you'll usually be working with fx is equal to either 3, let's start with let's start with the easiest one, 2 to the power of x, or fx is 3 to the power of x. And if you think about it, if you were to start substituting things in for x, you'll notice that 2 to the power of 0 is going to give you 1. You can check that on your calculator. 2 to the power of 1 will give you 2. 2 to the power of 2 will give you 4. 2 to the power of 3 will give you 8. 2 to the power of 4, 16, 32, 64, and etc. And all of a sudden, you'll notice that this starts getting, it starts increasing at a faster and faster rate. That's what an exponential is, but the main thing about it is, to be able to recognize it, is that it's your power changing. Your a here is going to stay the same, but your x here is going to change the whole time. And what that looks like in a graph, and like the fx is equal to 2 to the power of x, and this one over here, they're similar in how they look as a graph. If I was to graph this on a number line, well, actually, do you know what? If x was 0, my first point would be there, second point. My graph would end up going up really, really quickly. And I'm only doing this as a rough guide. We will be looking more into these in our graphing functions video next. But I just want to give you an idea of what it might look like. If you started substituting in minus numbers, what happens in the minus part of my x-axis, so that's my x-axis, that's my y-axis, is that my graph turns to something like that. And it'll get closer and closer to my y-axis, but they never will actually meet. We will have a look at those more in my graphing functions video, as I said, but for our exponential functions, being able to identify them is the main thing for our paper 1 and for our junior cert in general. Okay, I'm going to take a small break there myself, and I'll be right back to do... No, I don't want that. And I'll be right back to do to finish off this video. All right, just to finish off, we're going to have a look at one more exam question, and in my next video, as I've said a couple of times, we'll have a look at graphing functions. So 2018 question 8b, this question came up, and you're asked to identify, well, which graph lined up with your function up here. So I'm just going to write your function out again. Your function was up here at the top. Oh, and they've given you two pieces of information here. We'll have a look at that in a minute. You have x squared minus x minus 2 is equal to 0. So that right there is your function. And you need to be able to tell me about what's going on here. So if you remember back to our quadratics, we know that seen as my coefficient of x squared here, so my number before my x squared, seen as that's positive, I know that my graph is going to look like this. Now right now that doesn't help me because graph A, B and C all look like that. So we need more information. We've used our A. We know something about C though. We know that that's our y-intercept. So if we look at our three graphs, we need somewhere that crosses the y-axis at -2. And if you have a look, graph A crosses the y-axis at -2. And if you look at graph B and graph C, straight away, they do not do the same. So with just that piece of information, you know that graph A has to be your answer, because it's the only one of those graphs that crosses the y-axis at -2. We have, we've answered the question now, and we'll get to our justification in a minute, but there is piece of information there that will help you out. Just make sure that graph A is our answer. And you're told that the solutions of the equation where x is equal to -1 and x is equal to 2. What they've actually done is they've factorized your quadratic up top here, and then they've got the roots. So your roots or your solutions are the same thing. And if you remember what I was talking about a couple of minutes ago, your roots are where your graph crosses the x-axis. So if you look at graph A, x is equal to -1 and x is equal to 2, well, that's exactly what they're talking about. You'll notice that graph B and graph C do the same thing, but seeing as they did not cross the y-axis at -2, well, they couldn't be the right ones. This one here, graph A, is perfect. So we have to justify our answer. So just to finish off this question, y-intercept is -2, roots are -1 and 2, and so that's like our proof, but we need to sort of justify it. Graph A is only graph that matches up. That matches up. So being able to identify your quadratics or any sort of function in a graph is really, really important, and it really comes into play when you're graphing them yourself and when you're asked questions about the graph that you've actually done. Okay, I'm going to stop right there. Your key points are as follows. I'll put these in the description as well if you want to take those down. I'm not going to talk through all of those because I'm tired. I'm tired. I've been talking for about 45 minutes. And I've said the same thing throughout the whole video there. So just make sure that you're okay with everything in this slide here. As I said, this heavily links to your patterns video, and I'll put a link to that in the description. And my next video will be about graphing functions, so just keep tuned for that because it heavily ties in with what we've done today. Alright, we'll leave it there. Let's see. If I could knock this off now, that would be great. Alright, take 2. We will leave that there.